You're sitting on a plane. Somewhere beneath you, inside those wings, there are up to 180,000 litres of fuel. And that fuel, the substance keeping a 500-ton machine airborne at 40,000 feet, is essentially the same material that people used to light oil lamps over a century ago. Kerosene. Not gasoline, not diesel, not any of the more powerful, more widely available fuels that power almost everything else on Earth. Kerosene. And when most people hear that, their first reaction is the same. That makes no sense. Gasoline is more powerful. Gasoline is cheaper. Gasoline runs every car on the road. Why would the most sophisticated transportation machines ever built be running on lamp oil? The answer involves one of the most dangerous phenomena in aviation physics, a temperature so extreme it turns fuel into wax, and a function of jet fuel that almost nobody outside the aerospace industry knows exists. Stay until the end. Because the last point reveals something kerosene does inside a jet engine that will completely change how you think about aircraft fuel forever. 1. Gasoline doesn't fail because it's weak. It fails because it's too volatile. This is the assumption most people get wrong immediately. The instinct is to think gasoline is more powerful, so aviation must use something more refined, more sophisticated. The truth is the opposite. Aviation avoids gasoline not because it's too weak, but because under the conditions of high-altitude flight, it becomes dangerously unpredictable. Here is what happens. At cruising altitude, approximately 10,000 meters above sea level, atmospheric pressure drops to roughly 26% of what it is at sea level. At that pressure, liquids behave differently than they do on the ground. They evaporate faster. They transition from liquid to vapor at lower temperatures. Gasoline, which already has a very low flash point of around minus 43 degrees Celsius, evaporates aggressively under low pressure conditions. As it evaporates inside the fuel lines, it creates vapor bubbles, pockets of gas inside what should be a continuous flow of liquid fuel. Engineers call this vapor lock. Imagine drawing water through a straw that has air bubbles trapped inside it. The water no longer flows smoothly. The suction breaks. The flow stutters and stops. Now imagine that straw is the fuel line feeding a jet engine at 40,000 feet. The engine requires a continuous, uninterrupted flow of liquid fuel to maintain combustion. When vapor lock occurs, the fuel flow becomes irregular, the combustion becomes unstable. In the most serious cases, the engine stops, at 40,000 feet, over the middle of an ocean. Gasoline was not rejected because aviation needed something stronger. It was rejected because gasoline, under the exact conditions of commercial flight, becomes a reliability catastrophe waiting to happen. 2. A fuel that ignites too easily is not a feature. At scale, it is a catastrophe. Here is the number that ends the gasoline conversation on safety grounds alone. Gasoline has a flash point of approximately minus 43 degrees Celsius. That means at almost any temperature a human being has ever experienced, gasoline is already producing ignitable vapors, a spark, a static discharge, a small electrical fault. Any of these is sufficient to ignite gasoline vapor. Kerosene has a flash point of between 38 and 72 degrees Celsius. You have to actively heat kerosene before it produces enough vapor to ignite. At room temperature, kerosene is remarkably difficult to light. There is a well-known demonstration in aviation engineering education where an instructor drops a lit match directly into a container of jet fuel. The match goes out. The fuel does not ignite. Try that with gasoline. The result is very different. Now consider the scale. A fully loaded long-haul aircraft, a Boeing 777 flying from New York to Tokyo, carries approximately 100 tons of fuel. That fuel weight can account for nearly 1/3 of the aircraft's total takeoff weight. 1/3 of the aircraft is fuel. If that fuel had the ignition characteristics of gasoline, the consequences of any electrical fault, any fuel leak, any structural damage causing friction, would be catastrophic at a scale that no safety system could reliably contain. Kerosene does not just reduce fire risk. At aviation scale, it is the difference between a manageable emergency and an unsurvivable one. 3. At cruising altitude, the wrong fuel doesn't just stop flowing, it solidifies. This is the point most people have never considered, and it changes the entire conversation about why kerosene specifically, not just any non-gasoline fuel, was chosen for aviation. At cruising altitude, the outside air temperature is typically between minus 50 and minus 60 degrees Celsius. The wings, where the fuel is stored, are directly exposed to that cold. the metal of the wing structure conducts that temperature directly into the fuel tanks. Most common fuels, including many grades of diesel, would begin to solidify at those temperatures. Wax crystals form in the fuel thickens, flow slows. Eventually the fuel lines become obstructed. An engine that cannot draw fuel from its tanks does not produce thrust. Standard jet fuel, Jet A and Jet A1, is specifically engineered and chemically treated to remain fully liquid at temperatures as low as -47 degrees Celsius. Special additives suppress the formation of wax crystals. The molecular structure of the fuel is refined to maintain viscosity at temperatures that would turn most other fuels into gel. This is not a minor technical detail. This is one of the most critical engineering specifications in aviation fuel standards, and it is one of the primary reasons that aviation fuel goes through additional refining and additive treatment after the basic kerosene fraction is extracted from crude oil. The fuel in those wings is not kerosene in the way your grandfather's oil lamp used kerosene. It is a precisely engineered aerospace material that happens to be derived from the same crude oil fraction. If this is changing how you think about the engineering around you, hit the like button and subscribe. We explain aviation science clearly every week. 4. From every barrel of crude oil, only 10% becomes jet fuel. That changes everything. Here is a fact that surprises almost everyone who hears it. A standard barrel of crude oil contains approximately 159 litres. From that barrel, after fractional distillation, after refining, after additive treatment, only around 10%, roughly 15 to 16 litres, meets the specifications required for jet fuel. The remaining 90% becomes gasoline, diesel, liquefied petroleum gas, heating oil, and dozens of other products. 10%. That scarcity has direct consequences for aviation fuel supply chains, pricing, and the relentless engineering pressure to improve fuel efficiency on every new generation of aircraft. It also explains why aviation fuel costs are so significant to airline operating economics. Fuel typically represents 20 to 30% of an airline's total operating costs, and why every percentage point of fuel efficiency improvement in engine design translates directly into hundreds of millions of dollars across a global fleet. The 10% yield from crude oil is not just a chemistry fact. It is one of the foundational economic pressures that drives aerospace engineering forward, pushing engineers to extract more thrust, more range, and more efficiency from every litre of a fuel that is inherently limited in supply. 5. Before it burns, jet fuel does something inside the engine that almost no one outside aerospace knows about. This is the point that changes how almost everyone thinks about aircraft fuel. Inside a jet engine, the combustion chamber and turbine sections operate at temperatures exceeding 1000 degrees Celsius. At those temperatures, without active cooling, the metal components of the engine would overheat, warp, and fail within minutes. Modern jet engines use sophisticated cooling systems to manage these temperatures, and one of the primary cooling mechanisms involves the fuel itself. Before jet fuel reaches the combustion chamber to be burned, it is routed through passages that run adjacent to the hottest sections of the engine. As the cool fuel flows through these passages, it absorbs heat from the surrounding metal, dropping the temperature of critical components before they can reach dangerous levels. The fuel acts as a heat exchanger, a coolant, absorbing thermal energy from the engine and carrying it into the combustion chamber, where that energy is released as part of the burn. This means jet fuel is doing two completely separate jobs simultaneously. It is cooling the engine on the way in and powering it on the way out. No other commonly available fuel has the combination of thermal stability, high flash point, low freeze point, and heat absorption capacity required to perform both functions reliably under the extreme conditions of sustained high-altitude flight. Kerosene was not chosen for jet engines because it was familiar or cheap or available. It was chosen because nothing else could do everything the job required. 6. What this fuel actually represents. The next time you board a plane and you feel that faint smell in the jetway, that distinctive kerosene scent that every frequent flyer recognizes, you're smelling one of the most precisely engineered substances in the history of transportation, a fuel that resists ignition until it is supposed to ignite. That stays liquid at temperatures that would freeze most things solid, that flows steadily through fuel lines at altitudes where gasoline would vapor lock and fail, that cools the engine on the way to burning in it. That was derived from a fraction of crude oil that takes a century of refining science to produce correctly. From oil lamp fuel to the substance that makes it possible to cross an ocean in 11 hours. That journey, from the kerosene lanterns of the 19th century to the wing tanks of a modern Airbus, is not just a story about fuel. It is a story about what happens when human engineering refuses to accept the limitations of what already exists and takes something ordinary and makes it extraordinary.